Alrighty, so let's have everyone just trickle in, and I am super excited here to introduce Professor Cecilia Aragon from the University of Washington for Design at Large. I'm going to keep this introduction as short as possible, otherwise it's going to be like 15 minutes, and then it's not time for a talk. But so she is currently professor in the Department of Human-Centered Design and Engineering at the University of Washington, and she earned a PhD in computer science from UC Berkeley in 2004, and her research is at this really wonderful intersection of data science and design and HCI and computer-supported collaborative work. And she's going to talk a lot more about it today, but those of you, many of you in here have taken my classes and the classes of some of us, other design faculty. And one slide I always put up in my classes is this kind of triangle, and it's from obviously our own biases, but my triangle is you get really good at programming and computer science, and you can get really good at design, and you get really good at data science and data stuff, like you'll just be unstoppable, and those people just like don't actually exist, except that we actually have one right here. And you're probably like one of the only people in the world who can actually claim to be an expert in all of those three areas. And moreover, she was, Cecilia is one of these rare people who was an expert in data science, both in practice and in research, a decade or more before the term data science had even come about. And for a lot of that work, she won, in 2008, I believe, right? She won the PCASE Award, the Presidential Early Career Award. And that is the top honor that the US government bestows on early career scientists. So that's like very few people you'll meet have had that award. So it's a really huge deal. And I'm just really excited to have her come here because data science and design are two things that we're thinking a lot about on this campus. So I'm really excited for this talk.
Thank you very much for that rock star introduction, Philip. Thank you all for coming, and thank you for inviting me here. I'm super excited to come to this department, which I'm not going to give an adjective to describe because it's too exciting a place to be. I didn't say interesting, Taylor. So I'm honored to come here too because not only is your department interdisciplinary, but I've followed a lot of your research for many years and have based much of my research on some of the work that's been done here. So it really feels like I'm coming to the source of some of the most important ideas that I have worked on over the last couple of decades or so. So additionally, as you'll see in the talk, that I not only study interdisciplinary collaboration, I'm a passionate advocate for interdisciplinary collaboration as a way to address some of the most pressing issues that we're facing in the world today. Finally, I want to say that coming from Seattle, it's a pleasure to be here. I mean, I saw this big yellow thing in the sky, which I'd forgotten what it's called. And everybody here was saying, oh, it's cloudy. I'm like, cloudy? I can see shadows. That's not cloudy. So anyway, so I'm going to be talking about what I call human-centered data science today. And before I get started, one thing I always do when I talk to an interdisciplinary audience is I want to find out how many of you are from cognitive science? Okay, a large group. All right. How many of you consider yourself more of a sort of software computational person? Okay, all right. How many consider yourself a social scientist? All right. What about something else? Well, if you were going to speak about the work you do, how you would align yourself in a discipline, what are some of the other places? Design. How many of you would you consider yourselves designers? All right, okay. Large group. What else?
Statistics.
Statistics, yes. Who else here does statistics? All right, great. Yeah, I had a minor in statistics from UC Berkeley. Not that I use it that much now, but all right. Anything else that I haven't mentioned? Communication? Ethnographer, yes. All right. Any other ethnographers here? Okay, just a few. How many of you know what the word ethnography means? Okay, good, because I'm going to be using it in my talk, so that's great. All right. Okay, so thanks to Philip's great introduction, I don't have to give you the long version of my background, but I always do like to start out addressing an interdisciplinary audience with where I came from. So yeah, my degree is in computer science, and I actually have about 15 years of experience working as a software developer and data scientist in industry and government labs. And I did that before I came to academia. So I have it's a non-traditional academic background, but I think it's actually strengthened my research to have that practical experience. And the other thing I want to say is I started out in math and very hardcore software engineering. And I was, okay, I'm going to admit it, I was one of those people who didn't think the human interface really mattered. I thought if it was hard to write, it should be hard to use. And of course, what did I discover? That it was the human interface that really mattered. And if nobody uses your tool, it doesn't matter how elegant it is and how efficient it is, it's going to be dead in the water. So I have switched over, and now I am passionately human-centered. As a matter of fact, when I speak to computer scientists, I always say that I believe HCI and the human-centered piece of computer science is the big growth area in this field, in the computer science field. So, all right, let's start by talking about definitions. So what is data science? Does anybody here have a definition for me? What's data science? I mean, there's no wrong answers. Just to let you know, I'm a part of a large data science initiative at the University of Washington. And when we started out, we said, let's take a survey and make sure we have a definition for what data science is, since we're calling ourselves the data science environment. So we did. We took a survey, statisticians, computer scientists, designers, social scientists, biologists, astronomers, and you can kind of guess what happened, right? The answers were mutually exclusive. So I'd like to hear what some of you think data science is here. Yes?
Put simply, it's an appreciation of the data life cycle.
An appreciation of the data life cycle. Oh, I like that. I like that. That's a nice definition. Anything else? Yes?
Understand what is in the data.
Understanding what is in the data. That's actually a very good definition, because if we don't understand what's inside the data, it's meaningless, right? We have to transform it into human insight. Great definition. Any other definitions of data science? All right. Okay. Well, I'll give you one here that, well, this is they said big data is like teenage sex. Everyone talks about it. Nobody really knows how to do it. Everyone thinks everyone else is doing it, so everyone claims they're doing it. And that's actually pretty true. At least that's what we've found at the University of Washington. So, all right. So the phrase big data, all right, so when I've used this phrase, people scoff and say, oh, that's so 2012. And yes, it was a buzzword, but I still think it's an interesting concept to look at and unpack a little bit. So does anybody have a definition for what big data is? Yes?
Any data set you can't open in Excel.
Yeah, I love it. Any data set you can't open in Excel, that's great. Anything else? Yes?
Some data set that is some order of magnitude larger than what you had previously been dealing with.
Okay, Taylor, you have been peeking at the answers. Yeah, we have a plant from UW, right. I think that's a great human-centered definition. And I'm not even going to mention volume and variety and velocity. Yeah. So I like to use this human-centered definition of big data as it's 2 orders of magnitude greater than what you're used to dealing with. So about 100 times more. And the reason why this matters, if you're looking at a human-centered perspective on big data, is that is about the level where you have to totally change whatever procedure you've been using. If you had software that was dealing with data 100 times smaller, you have to completely rewrite it. If all your daily routines will have to change. So I'll give just a couple of examples. So the Large Synoptic Survey Telescope in astronomy is the world's largest digital camera. It's going to have first light in 2020 in Chile. And they're going to be looking at 10 terabytes of data per night. And this is a big jump in the field of astronomy from about 100 gigabytes to 10 terabytes. So they have to completely rewrite all their software pipelines. It's a major effort. They've been writing the code for many years. Physicists of the Large Hadron Collider in CERN, well, particle physicists have already said they have big data before anyone else did. And if you look at just the number, the actual number, 20 gigabytes per second, it's a huge amount of data that they need to process. And again, as they jumped, they actually had to build this whole giant particle accelerator. I mean, not to handle the data, of course, but to generate the data. So another really huge paradigm shift. But I want to bring this down. These numbers, gigabytes, terabytes, exabytes, petabytes, and what does it really mean? I mean, it's hard for us as humans to really intuitively understand these very large numbers. So what I like to use as an example, it's like, let's suppose you were a humanities researcher and you had to read 2 books per week to do your work, and now you have to read 200 books per week. Okay? What is that going to require? Obviously, you can't physically read 200 books a week. I mean, so in the field, they've talked about going from close reading to so-called distant reading, where you don't actually read. And that's a very controversial topic, which is out of my field, so I'm not going to discuss it. But the point is, this 2 orders of magnitude growth is what almost all fields are facing today. And so it's really, this is why there's been all this talk about data science and big data, because people are being deluged by data. They're being overwhelmed by it. And something needs to be done, and we really don't know what it is. And I hope to convince you in this talk that it's a human-centered perspective that will give us one of the best angles into figuring out these problems. So I'm not the only one who's talked about this. There are many others who've mentioned the fact that there's this definition of big data as being, it's only big if it's very high numbers in velocity, variety, and volume. And, okay, what happened there? Oh, thank you. That's a relief. And it's been pointed out, it's also been pointed out at the same time that there are a lot of people with much smaller data sets, like this humanities scholar that we were talking about with 200 books per week. That's, that's nothing, right? That's a few gigabytes. And is that really big data? And I would say yes, it is. So if you're looking at all these different, ways of looking at data, we need to address data at all these different scales. So this is one argument for why human-centered data science, but I also want to give an argument more in terms of sort of a more logical argument. I think this argument comes more from my computer science and math background. So we know that we want to look at what's the rate-limiting step in data understanding. And we know the amount of data in the world is growing exponentially with unbelievably large numbers. But we also know that according to Moore's law, computational processing power is also increasing exponentially. So you could say, well, what's the problem? We're always going to be able to build better tools to do it. We're going to move everything to the cloud. We're going to parallelize. We're going to be able to keep up with it. And of course, the answer is that's not quite true. There's a law in computer science, Amdahl's law, that says that the speed up is only based on what is perfectly parallelizable in the software. And that's, of course, not everything. So no matter how much you put your software in the cloud, you're not going to gain this exponential growth in terms of dealing with it. So this is the picture as it's often drawn, though, when you talk about what are the gaps that we need to address in data science. But I think, of course, that there's something really important missing, and I'm sure all of you know what it is. The human, exactly. Because human cognitive capacity is not increasing exponentially. As a matter of fact, I would say it's constant, although my teenage kids say I'm wrong. They say they're a lot smarter than me and they can multitask better. And maybe they're right. So that's why I gave this line a little bit of a linear growth path. Because I got to keep my kids happy. And it's probably true. You know, let's hope that over time we are becoming smarter as a society, although sometimes I think there are setbacks on that. But we'll not mention that. I'm being recorded, right? But anyway, but no matter what, human cognitive capacity is never going to grow exponentially. And so we need to deal with it with more than one gap. We need to deal with I'm not saying, when I talk to computer scientists and statisticians, they want to say, but our work is really important. And I say, yes, of course it's really important. But it's well understood that your work, building new hardware and software and new statistical algorithms, new machine learning algorithms, all that needs to be done. But in addition, we need to look at this human-centered data science piece. We need to look at how do people collaborate? How do they collaborate over software? How do they deal with each other in groups? We need to look at visualization. Visualization is the highest bandwidth channel. The visual system is the highest bandwidth channel into the human brain. It's a wonderful way to get very large amounts of information directly into the gray matter. Visual analytics, combinations of looking at the visualizing material and using machine learning to make to kind of build a human-machine collaboration where the humans are contributing the piece that they're good at and the computer is contributing what it's good at. And then, of course, there's all the associated issues with ethics. There's so many really important and critical ethical issues in data science that must be addressed. And we are only beginning to scratch the surface. We need to look at the impact of data science on society. We need to apply sociological principles. We need to use ethnography. We need to bring in the techniques that we as humans have developed over centuries of studying, of developing knowledge and studying the world around us. And it needs to be interdisciplinary, kind of like what you guys do here. I'm going to take I'm going to show just a couple of interesting slides on collaboration because I think it's a really important topic and one that needs more research. I'm hoping that people are going to continue to work in this area. Certainly there's been a lot of research on it so far, but I think not nearly enough. So if you look at just the maximum number of authors on a single paper by year, there's been this dramatic growth. This term hyper-authorship was coined by Indiana University information scientist Blaise Cronin, and he's talking about these papers that have thousands of authors on them. All right, so this physics paper here was from the Large Hadron Collider, so you had 3,000 authors, 3,000 physicists, because they all participated in building this giant particle collider. All right, and so they needed to get credit, so they need to contribute to the paper. And with medicine, that was a paper that was federated. So you do a cancer study, and you want to get the data from all these hospitals around the United States. And so everybody contributes a piece of the data, and you want to give the people who contribute credit for that, for the work they've done as well. I keep saying it. All right. Taylor has this thing where he says you're not supposed to use the word interesting. So I'm going to try to avoid it, but it's really hard for me. It's like unpack the word. Unpack the word, yes. So it is intriguing to me that that about 10 years ago, 1,000 author papers were unheard of, and now they are more common than 50 plus author papers were in I think it was 1981. All right, so a 1,000 author collaboration is more common than a 50 author collaboration was in 1981. Okay, all right, I mean, something pretty dramatic is occurring here. And I think part of this is because collaboration is really essential. this large amount of data, these complex problems, it's more than one person can understand in a human lifetime. We are entering this very collaborative world now. And I could talk about this for several hours, so I'm just going to do it very, very briefly, just to say that we need to combine different skills to really understand what's going on. We have to build interdisciplinary teams, and this is because we have these vast and complex and challenging scientific, social, political, and human problems that we really need to start figuring out and moving toward answering. But the problem, of course, is that collaboration isn't so easy. You know, you don't just put 100 people together with 100 different skills and say, solve this problem. It doesn't work that way. There's been a lot of work in collaboration that has shown that many barriers are social, not technical. We really don't know enough about the dynamics of complex work teams. Despite all the studies that have been done on it, it's not enough. We need to know more. Distributed work is very difficult. Distance matters. And we really need to study more how to foster these productive collaborations. So shifting from the more theoretical down to the practical, at the University of Washington, we have the eScience Institute, which was started about 10 years ago by Ed Lazowska, Tom Daniel, and Werner Stützle. And they saw that there was this deluge of data approaching in all these fields kind of early on when not that many people were aware of it. And they said data-intensive science is going to be ubiquitous, and it's really important to note that it is about people and software and not just hardware. At that time, it was believed that all you have to do is build a supercomputer, and that will solve all your problems. And as we all know, as you all know, that's really just the beginning, if even a possible solution. So at the University of Washington, in partnership with UC Berkeley and New York University, there are about 20 of us who are PIs on this large grant from the Moore and Sloan Foundations. And our goal is to look at data science in academia and figure out what can we do to make it more effective. And the idea that we came up with on our proposal was to create this virtuous cycle. Right? So we picked several scientific theme areas: biology, environmental sciences, physical sciences, and social sciences. And then we looked at all the methodologies from statistics and computer science and design and human-computer interaction. And we noted the fact that when there are these big fundamental problems in these sciences, what they tend to do is they spur really interesting research. I mean, so this is kind of not the way research is normally done in academia. I know that when I was first starting out, I got comments like, "Oh, your work is too applied," and I said, "What?" I mean, to me, I feel that it's the fundamental discoveries that we can make in computer science and in these methodologies and statistics comes from these really wicked problems in these scientific fields. It's by addressing these really important problems that we can come up with new ideas and new algorithms and new research. So this is what we've discovered. And then we find that as we build these new tools, as we come up with new algorithms, that goes back into this cycle and also transforms discovery. And so you have this virtuous cycle. And I'm going to give you an example of this happening from my own work. All right, so I'm not just saying that this is a good idea. This is really true. And this can lead to prize-winning research. All right, and so these bridges in between are how we operationalized it. So we have these 6 working groups in various different areas. And I'm going to talk about them very briefly, but I want to stay on time here. This is the University of Washington campus, and these are the PIs to show you how interdisciplinary this grant was. And these are the people in the eScience Institute Steering Committee, and these are the participants in our data science initiative. So the point I want to make is that this interdisciplinarity is really what's necessary in order to move forward in discovery today. All right, so now one of the things I'm especially proud of about this initiative is that when we started doing all this, we decided that we were also going to be reflexive. We were going to take an ethnographic view of the data science as we were doing it. So this was really kind of unprecedented, because most of these very large grants are formed to do, it's like, we're going to do science. We're going to come up with, with the equation of state of the universe. We're going to discover a new particle. And what we wanted to say is, yes, we are going to do that sort of thing, but we're also going to study how we do it. We're going to observe our mistakes as well as our successes, and we're going to really look into the collaboration. So, some of the work that we have done has been where we really have tried to look at, boots on the ground. What are the factors that contribute to collaborative dynamics? As I said, there has been a great deal of work done in this area, but there hadn't been anything done specifically in this type of large data science collaboration. So, by the way, all of these slides, I know I'm going through them sort of fast, but they all have papers behind them, and they're all available on my website. So I'm always open. You can talk to me about it, too, if you want afterwards. But one of the things we noticed, of course, which shouldn't come as a surprise, is that data science involves solving both technical and social issues. And I keep saying this, and the reason is that you'd be surprised at how many people don't agree with this. All right? And so often what I've had to do is I've had to produce evidence that, that there really are social issues and that a human-centered approach is an important way to address technical problems. And so I'm going to give you an example from my own work. This is in astrophysics. So these are four new ideas that were generated for this astrophysics collaboration. And they all had to do with building software and coming up with new algorithms. But what's really important is they all were discovered by a human-centered approach. I came in and I did an ethnographic evaluation of this group, and I used what I learned from this to help to develop insights to build software that made the collaboration more productive. So due to time constraints, I'm not going to go into a lot of information about the science, but it's very, very cool. Essentially, this astrophysics group was working on fundamental questions about the nature of the universe, and questions that Einstein looked at over 100 years ago and came up with this idea of a cosmological constant, which he later said was his greatest blunder. And then it turns out that maybe he wasn't wrong after all. So I'm so tempted to go into the... Should I tell the story? It means I'll skip some other ones later. Do you want to hear the astrophysics story? Or, all right. All right, OK. So when Einstein was coming up with his general theory of relativity, he said, oh, there's one problem. There's gravity in the universe, and everything should be drawn together in a great big ball. So why doesn't the universe collapse? And so he said, oh, there must be some miraculous force in the universe that sort of spreads everything out a little bit. And I'm going to call that the cosmological constant, because if I put this lambda in my equations, everything works out beautifully. Okay, he had tremendous success with that, with special relativity and then with general relativity. So why not? But then, not too much longer after that, the astronomer Hubble said, oh, he discovered by observing galaxies and looking at their redshifts that the universe was actually expanding. And this wasn't known back then until Hubble discovered it. And so Einstein said, oh, there's no need for lambda. The universe is expanding, so that's why gravity isn't causing everything to collapse. It will. It's just that it's expanding now, and eventually it'll all collapse on each other. So, there was no need for lambda, and that's when Einstein said it was my greatest blunder. But then, of course, the obvious question is, well, when will the universe contract? Obviously, it must. So let's measure the deceleration rate. So this was the conventional wisdom all the time I was growing up, certainly, for 70 years. And then in the 90s, two different astrophysicists, independently made this shocking discovery that if they hadn't done it independently, everybody would have said they had an error in their calculations. They said, no, not only is there no deceleration rate, the rate of expansion of the universe is actually increasing. Like, oh my God. But why? So why is this happening? Rees and Perlmutter won the Nobel Prize in 1998 for discovering this mysterious substance in the universe called dark energy, which actually acts as this, repellent force and kind of pushes. Okay, I'm totally mangling the physics, but that's essentially the idea behind it. And the way they discovered this is by studying a certain type of supernova. These are the largest thermonuclear explosions in the universe. And what is really interesting is there's a particular type of supernova that always kind of explodes at the same time. It always looks about the same. And so what you can do now is you can use it as a standard candle. Because if you can recognize one of these types of supernova, when it explodes anywhere in the universe, you know how bright it's supposed to be, and that will give you a very accurate measurement of the expansion rate. So now, of course, the issue is, how do we find these supernovae? And when I joined this project, the common way that supernova science was done is, people would get funding to go out and, point your telescope at a particular area, and there's no way to predict where a supernova was. So sometimes you would see one, and one would be discovered maybe every few months. And then everybody would jump on it, and people would point their telescopes at it, and they would study it. And that was the mode of doing science that they had. That you had about a month, 2 months to study this supernova in detail. But in order to really collect enough supernova to address this issue, to have enough standard candles so that you could put good boundaries on the equation of state of the universe, you need to look at a lot of them. And so what you do is you image as much of the sky as possible. Essentially, so you take a large picture of the sky, and then you save it and you register it in a big database. And then every night you take another one, and what you do is you subtract the most recent night's image from all the ones you had before, and you're looking for these little bright spots that suddenly appear. And so if you look at, every night we would process this data, and we get about 600,000 of these little bright spots, and out of those bright spots, about 10 were probably supernova candidates. All right, so now I'm going to talk about these 4 techniques that I and others came up with in order to address this issue. So machine learning it's a powerful technique for classifying data. So we wanted to classify these images from either a supernova or not a supernova, all right? But there is a problem, because it turns out that if you have 600,000 objects and only 10 of them are supernova, what would your machine learning algorithm do? In order to be the most efficient as possible, it'll just say, oh yeah, none of them are supernova. And now I have 99.9999% accuracy, which is actually really good in the machine learning community. So what you have here, this is an unbalanced data problem. And I don't want to say that we came up with the solution to the unbalanced data problem. That was done before. But what we did is we were able to come up with a novel way of dealing with this imbalanced data and this class uncertainty so that we were able to dramatically reduce the number of false positives by a factor of about 90%. Right? So what this ended up doing is saving a lot of human labor, because when I first joined the project, there were about 6 postdocs spending 4 hours a day looking at these little images. And it was very frustrating, as you can imagine. They wanted to be doing science, not looking at little images and saying, is this a supernova or not? So the error that they had made before, and I was actually the third computer scientist that had been brought in to try to address this problem. And the error they had made before is they had said, we want to totally automate this process. Well, it couldn't be totally automated. There were still some things. Humans are wonderful pattern recognizers, and there's still some things where you need the human. We just needed to improve the algorithms so that the humans would only look at those smaller edge cases. And we were able to do this. And so we came up with this algorithm, we implemented it, and it dramatically improved their science. And in addition, it advanced the state of the art in machine learning, and we won a Best Paper Award for this work. So this is where I said that virtuous cycle is you can accomplish a lot in 2 different fields if you're really focusing on those key issues in that particular field. All right, so my background is in image processing, and I tend to, because I like it, I tend to talk a little too much, so I want to make sure I cover the whole talk. But essentially, the issue here is that this is a subtraction with a good supernova. That's a galaxy there. And you subtract tonight's galaxy from the galaxy and all the previous nights, and you get this nice round object, and that's possibly a supernova. As a matter of fact, that one actually is. But there's another problem, is sometimes you can get a star, and then in the image, it's close to the edge, and so this causes a misregistration in the algorithm. So you got this thing, which obviously is not a supernova. But the issue was that the physicists who were working on this were not image processing experts, and they didn't know that this was that this is a problem that has been solved before. The Fourier contour descriptor algorithm can easily address this issue. And so I suggested it. And the first thing, as soon as I said Fourier, all right, their faces all fell. We can't use Fourier analysis. It's too slow. It takes too much time. Our program is running all night. We don't have time for any more increases in the running time. So I came up with a really fast algorithm that essentially ran in constant time. The bottom line is there was no measurable increase in the running time, and we had a 41% reduction in false positives. And the important thing to note is that I would not have come up with this if I had not sat with the scientists and taken a more ethnographic approach, a slow approach. Everybody else who had come in had just said, oh, what are your requirements? Let's be efficient. Let's do this. And they had missed some of these important issues. All right. So those were 2 more technical algorithmic approaches. Let's now look at the social side. So I'm going to skip one of these and go straight to the next one just to keep in time. So there are 2 of them. And I want to talk about this was a really interesting problem. All right, so the astrophysicists who were looking at the supernova were part of a collaboration of about 30 people, about half in the United States and half in France. And they operated a telescope in Hawaii that looked at each of these particular supernova, and they coordinated via chat, via instant messenger, actually. So they had this little chat log in their window as they were operating the telescope, and they communicated back and forth with that. And one of the interesting problems, oops, I said it, was that the most senior scientist was in the United States, and he was the one who understood the telescope the best. And it had this really kludgy interface, which, yeah, I'm not going to talk about that. Anyway, it was not human-centered. And so he was really the only one who understood this interface. And what would happen is the junior scientists in France were the ones who were doing a lot of the observations simply because it was daytime in France while it was nighttime in Hawaii. So they would be doing this, and then this senior scientist would wake up in the morning and no data had been collected. And this was very frustrating to him, you know, because there was a lot of money and effort and time going into this. And so he would say, well, what's wrong? And they said, well, there was this problem with the telescope. And so he said, look, just wake me up. You know, if there's a problem with the telescope, wake me up, I don't mind. And he said, I'm putting my phone by the side of my bed, call me. And then the next night would happen, and nobody would call him, and there was no data. And so what we did is we built a little chat bot, a really simple chat bot. And if someone typed into the chat SOS and the name of any member of the collaboration, it would send a text message to their phone. All right? And so if they typed in SOS and the name of the senior scientist, it would text him. The phone was by his bed. It would wake him up, and he would get up, he would get in the chat, and he would solve the problem. All right? And that simple change caused a four-fold increase in the amount of data collected. Right? And this paper we tried to understand why that happened. But basically, it was that, you know, these were grad students and junior scientists who were kind of intimidated by this senior scientist, and they didn't want to call him up and they didn't want to wake up a senior scientist in the middle of the night. But if you texted him, that was okay. All right? So, you know, these affordances, I mean, I make this as an example to show that technological affordances can make big differences in human-centered collaboration. It doesn't have to be a complex answer. Sometimes it's understanding the human processes underneath is all it takes. All right, so the bottom line for this was that I came in and I took a human-centered approach to addressing this data science problem. And with these four elements, we had significant measurable improvements. I have some other slides from this too that talk about the labor savings. One of the ones I like the best is it shows the number of papers they wrote. Went from, you know, 0 before I came to, you know, several dozen a year at the end. And of course, I can't take credit for all of this, but I do want to mention this, that our principal investigator won the Nobel Prize in Physics after this project was complete. And again, I cannot take credit for this at all, and I don't want to say that. But Saul Perlmutter did say when he received his Nobel Prize that it was a team effort, it was a collaboration, and he did mention me as one of the names. And it's the closest I'll ever get to a Nobel Prize, so I will take it. Thank you. I'm not used to getting applause in the middle of the talk. All right, so now I'm going to switch gears to my current work. All right, and this is something, so I kind of tend to like to champion these unpopular causes. All right, so when I was doing this work in about 10 years ago with the astrophysics community, I was the one who was saying, human-centered approach is really important. And they was, oh, Cecilia, what's wrong with you? You know, that's soft. It's not very important. It's not very good. And I said, hey, but look. And so now I'm going to propose another human-centered approach. I would like to talk about this vast, underexplored resource of human-generated text data. And this is my current area of research. And although there has been a lot of work studying text, it's not nearly enough based on how much text there is and how important it is. Every day, we produce more text than we produced in human history up until 2013. I mean, this is just a huge amount of underappreciated data that is a trace that can tell us a lot about us as a society. And yes, it's not as sexy as images, it's not as exciting as video, but I would venture to say that all of you probably spend more time texting or using text communication than you do with video. All right? So this is just some of the interactions that we use text for. So, what can we learn from text data? There have been a number of really interesting, I keep saying this. There have been a number of really important areas of work studying text data. Obviously, we can look at human behavior, and we can come up with results, sometimes of better quality, sometimes of worse quality. We can examine societal trends. There's even been research looking at how Twitter can predict the stock market. Sometimes that works, and sometimes it's not. There's the famous case of Google flu trends. Does everybody remember Google? Who remembers Google flu trends? Okay, only about half of you. The idea was that Google said, we noticed that whenever the flu strikes in a particular area, everybody starts making searches about flu, about fever, about various flu-related words. And so they said, let's see if we can discover this trend and find out where the flu is going to hit, and then maybe tell the Center for Disease Control you need to send more vaccine to this particular area. So they did it, and it was this tremendous success. They hyped it, everything was great. And then you can imagine what happens, right? They said, we've solved the problem. We're now going to set the algorithm running and just leave it there. It's done. We don't want to waste human effort on it because we want to be efficient and we want people to work on other things. Of course, within a couple of years, society changed. That algorithm itself changed, and it became completely ineffective. So, without human intervention, without human attention to algorithms, you're going to have these. It's not going to work that well. The other thing that I think is really interesting is just some work about detecting earthquakes. The best way, of course, to detect earthquakes is to have lots of sensors all over the ground, and then to measure it precisely. Where's the epicenter? Where did the ground shake the most? But it turns out that if you look at Twitter and you look at the words that people mention, they're not as accurate, but there's a lot more of them. Everybody not everybody, but a lot of people who are involved in an earthquake start tweeting about it. And the words they use in their tweet indicate, approximately what the amount of the Richter, it is on the Richter scale, and they were able to. You can actually pinpoint the epicenter pretty well. All right, so those are just some examples. All right, so the research that we're doing in my lab now is we are trying to look at social media text data. And we want to look at both quantitative and qualitative approaches. That means we write software, we create algorithms, and that has the advantage that we can study a very large amount of data. It's very efficient. But of course, the bad is that it's really shallow and superficial. But we also, because our department is interdisciplinary, we have students in our department who are ethnographers, and that's their focus. And so they can take a deep textual analysis of a small amount of text data, and obviously the advantage there is they can get some deep explanatory conclusions. But the bad, of course, is one person can't read 10 million tweets. So how do we get the best of both worlds? What we are trying to do, what we're working towards, is combining these machine learning techniques with visualization, with qualitative research, and building tools that people can use to analyze this text data in a deeper and more nuanced way so that we can draw conclusions based on these large data sets but maintain this context and depth. And one of the key insights we've had so far is that when you're coming up with a machine learning algorithm, the efficiency of that algorithm is not nearly as important as its transparency and understandability. You know, if you're giving people parameters to tweak, those parameters should match up with their mental model so that they can understand what they are doing. And that makes these tools much more powerful. So, in conclusion, I hope to leave you all with this, that you're convinced that data science is a socio-technical ecosystem. And we need people from all disciplines, all walks of life to be studying these really complex issues. I know you had, and there are these areas of human-centered data science. I'm going to just give a very brief example, although I'm sure there are obviously many more, because I know you had Brian Granger. Yeah, so he talked about IPython and Jupyter, and this was really a tool. If you talk to Fernando Perez, who first came up with IPython, he took a human-centered approach to building this tool, and that's why it was so successful, at least in my opinion. I mean, because instead of just saying, I'm going to build this really cool piece of software, you know, I mean, I think a lot of Philip's work is also human-centered data science, because you say, what is it that people need? How can we build tools that fit in with the ecosystem of how people are already working, and how do we make it better? But I do want to leave you all with sometimes those of us in data science get a little too enthusiastic about the power of algorithms and the power of our approach to address issues. And as a result, mistakes are made. And sometimes these are very, very bad mistakes. Do I have time for one more story? I'm supposed to talk until 5? Yeah. Right? So I have about 8 minutes. All right, great. So just one more story. Who here knows about the New York Taxicab data story? Okay, just a couple people. All right, great. I'm glad some of you have heard of it. So I forget exactly what year, but it was a few years back. Somebody collected all the data of all taxicab rides in New York City. They said, oh, wow, this is a very cool data set. We want to release it to the public so that others can get benefit out of this data. But obviously, we want to protect people's privacy, so let's only put a little ID tag on each taxicab ride, and then people will be completely protected, right? Right? No? Who here has heard of differential privacy? Okay, just a few of you. All right. So those of you who haven't, you should look at differential privacy, because this is. The fact is that whenever you have a very large data set, you have to be very careful how you anonymize it. And if you are a person, who, as I am, who works with very large data, and we want to share that data, make it available to the public as much as possible, you have to be extremely cautious. Because what happened with this taxicab data is, yes, there weren't people's names associated with it, but you could look at ID number 527 and notice that from Monday through Friday, it went from this particular address to that particular address, like from home to work, okay? And except that every now and then it stopped at a brothel, all right? And all of these, you could identify a lot of people in this data set, and that is generally true. There have been many data sets that have been released to the public where people were identified. So we need to be careful. This is another extremely important part of human-centered data science, is taking the time to consider the societal impacts deeply, to think more carefully about it. Don't just say, I'm going to produce this algorithm and it's going to be great. People are biased, so my algorithm is going to be unbiased. No. Just a couple shout-outs. I want to shout out to Lily Irani and Six Silberman, who've done some very important work on Turkopticon and enabling workers in Amazon Mechanical Turk to get together, giving them a voice, really, when they had no voice before. As a question about design, Daniela Rosner from my own department at UW wrote a very intriguing article in Interactions in 2015 about what happens if you crowdsource design. And I'll let you look that work up. But essentially, the idea is that there was this one famous study of what are the best paintings. And so they crowdsourced it. And you can imagine, did they get, the Mona Lisa, Van Gogh? No, they got these really dull kind of landscapes because that was the least common denominator. So although crowd work can be very important, it's not a panacea. And I think this is something that human-centered data science is one of the questions that can address. And a lot of the people here who are working in computer science and algorithms maybe should partner up with people working in social science and anthropology and ethnography to really look at the ramifications of these socio-technical systems as we move into the rest of the 21st century. So I'm going to just conclude with that note that I chose the title of the talk, Hearts and Minds, very deliberately because of its connotations. The fact is that these are complex questions without simple answers. And understanding how humans deal with data science is going to be the best path forward in facing some of society's most pressing issues today. So I'd like to thank you very much for listening to me today.